interval we had shown that in the outer region of the flow the vorticity value is a constant along a streamline, and since the upstream is a uniform flow with a 0 vorticity, the value of this constant is 0. So, for any streamline which is starting any streamline in the outer region which is starting from the upstream region here, omega is 0. Now, we will give a physical interpretation to that. We will take a cylindrical element of fluid and so this is a fluid element, and we will consider its angular momentum about the center. So, we will put a coordinate system, local coordinate system with the origin at the center. If you look at the angular momentum, which I will call h about O in the z direction. Now, this you can show is the momentum inertia about O into omega z, where omega z is half curl of V z component. So, this gives a physical interpretation of the vorticity. Now, for an irrotational flow omega z is 0. That means, if you have a fluid element in the form of a cylinder in 2D incompressible irrotational flow, the angular momentum of this element about the z direction is going to be 0. Now, as the fluid is moving, its angular momentum could change if the forces acting on the fluid element exert a moment about O. So, we know that d dt of h 0 will be the sum of the moments about O. Now, if you are interested in the moment about the z axis, this will be z and this will be z. Now, let us see what are the forces on the particle. So, if I draw a free body diagram of this fluid particle which is in the form of a cylinder, you have a body force and surface force. Now, the body force will effectively act at the center of gravity. Now, we are taking a fluid where the density is constant. So, if rho is constant, we know that the center of gravity will be the centroid here, which is the geometric center, that means it will be at O. So, we can show the net effect of gravity as a concentrated force, which you can call the weight, which is mass of the fluid element into g, which will act at the center. Now, this force is not going to exert any moment about O, because it is passing through O. Now, let us look at the surface forces. The surface forces are exerted by the surrounding fluid outside this element on this. Now, if you look at the stress distribution, if you take a area element at any radial along a radial line here, this is your dl, let us say, you are going to have a normal stress and a shear stress. Now, if the shear stresses are negligible and the viscous normal stresses are also negligible, then the surface force on this area element is going to be simply the pressure at this point times dA, and it is going to be inwards, radially inwards. Now, this moment exerted by this infinitesimal force about O is also 0, because this line is passing through O. Similarly, I can take any other area element and we will see that the force due to the normal stress is going to pass through the centroid. So, the normal stresses, even if you consider viscous normal stress, if it is there, you will not exert any moment about the center. So, if you have a fluid particle which is somewhere here in the outer region, we have seen that viscous stresses are negligible here. The forces acting on this cylindrical element of fluid will not exert a moment about its center. So, its angular momentum about its center will be conserved, because then this is going to be equal to 0, the rate of change of the angular momentum, which means that the angular momentum at any time t will be the same as the angular momentum at t equal to 0, because the rate of change is 0, and initially we are saying it is irrotational, because the fluid particle is starting from a region which is irrotational. So, at t equal to 0 the particle was here, at a later instant of time the particle has moved this way. So, your h 0 is going to be 0, which means if h 0 is 0, that means omega z is 0. So, vorticity will be conserved along this particle and it will remain irrotational, that is the value of the vorticity will be 0. Now, if you consider a particle which is entering the boundary layer, okay, and if I draw over here a free body diagram. So, at this point let us say I take a fluid particle which is in the form of a circle, the cross section is in the form of circle and it is it has some length in the z direction. So, I am drawing an enlarged view of this and showing the forces acting on it. Now, if it is a viscous fluid, you are also going to have some shear stresses on the surface in addition to the normal stresses. Now, the normal stress due to pressure is not going to exert any moment about the center O, and the weight or the body force, that will also not exert any force or moment about the center, but if you will consider the shear stresses, they can exert a moment about the center. So, now the net moment exerted by the forces acting on the fluid particle is not 0. So, you are going to have d dt of h 0 z, which is the sum of moments about O in the z direction. This is not going to be equal to 0, that means h 0 z t will not be equal to h 0 z at t equal to 0. Now, at t equal to 0, the particle started from a region where the vorticity was 0, that means h 0 this might be 0, but once it enters the boundary layer, shear stresses will start acting on the particle, they will exert a moment over the center, it will change its angular momentum, and once the angular momentum changes, you see that omega z will be non-zero, that means vorticity will be generated. However, if you look at the outer region, it remains irrotational. Now, let us see what is the utility of this. So, we are looking in detail at the flat plate viscous flow past the flat plate. Upstream velocity profile is infinite, is a uniform flow, the speed is u infinity. Now, the solution of the Navier-Stokes equations is difficult, you cannot get an analytical solution. So, what we are trying to do is following Prandel's idea, and we are dividing the flow field into two parts. We are calling an outer region and you have an inner region. The inner region is referred to as the boundary layer. Now, what we are doing is, in the outer region we are making a approximation, and the Navier-Stokes equation which I am denoting by NSE is being approximated by Euler's equation. Now, Euler's equations are for an inviscid fluid and this is a viscous fluid. However, we have seen the viscous effects are negligible here. So, if you solve Euler's equation in the outer region, it will give you a good approximation to the flow, but inside in the boundary layer region you cannot neglect the viscous effects. So, here what we are doing is the Navier-Stokes equations are being approximated by what we had derived last time, Prandtl's boundary layer equations. So, we are making two different approximations in the two regions. Now, I would like to emphasize that in both the regions the governing equation is the Navier-Stokes equations, which I am writing as NSE. So, this is the Navier-Stokes equations, but we cannot get an analytical solution. So, we are trying to simplify the analysis by making approximations. We do not have one set of approximate equations which can describe the flow everywhere. So, we have two different approximations in the two regions. Now, Euler's equations are not easy to solve, but as we have seen for this particular case, when the upstream is irrotational, the flow here remains a potential flow, because vorticity remains 0, and the solution procedure for potential flow we have already discussed. So, by solving linear equations you can find the flow field in the outer region. Now, what remains is the job of matching the two approximations. So, what we will do is we will take an intermediate region or overlap region which includes the outer part of the boundary layer or inner region and the inner part of the outer region. So, we will call this the intermediate region. And we will insist that the solutions obtained by solving these approximate equations will give you the same result at all points inside this region. So, first of all let us see what is the size of the regions. So, I will draw another figure here and let us say this is the boundary layer. Now, if you take a point here in the outer region, we are saying that y star, which is y by the length of the plate, is order 1. Now, the size of the or thickness of the boundary layer we have found, and here y star is y by L, which is y by delta naught by L by delta naught, and y by delta naught is what we had called capital Y. Sorry, this is y by delta naught into delta naught by L, and delta naught by L we have shown was R e to the power minus half, and y by delta naught is what we were calling y earlier. Now, we will introduce a small parameter epsilon, which is 1 by R e. So, what we have here is that in the boundary layer this is y star is a small quantity, it is epsilon to the power half into capital Y, and this capital Y is order 1. Now, in the outer region y star is order 1, which is epsilon to the power 0. So, if you look at the intermediate region over here, here your y star will be order epsilon to the power m, where m is greater than 0. If m is greater than 0, then this y coordinate in this region is going to be have a value which is less than the y coordinate in the outer region, and m must be less than half. Then it will be the y coordinate here will be larger than the y coordinate in the inner region. Now, I will show this again on an enlarged view. So, here we are saying y star is y by L order 1, which is epsilon to the power 0. Here we are saying, so this is the outer region. Now, in the inner region we are saying y star, which is y by L, is order epsilon to the power half. and in the intermediate region which I will show this way schematically, y star is order epsilon to the power m, and we are saying that m lies between 0 and half. So, here we defined an order 1 coordinate which was y star by epsilon to the power half, which is order 1. Here we can define an order 1 coordinate, we will call y intermediate, which is y star by epsilon to the power m. Now, in the inner region we will solve Prandtler's boundary layer equations and find that the non-dimensional velocity is some function which we will call u inner of x and capital Y, capital X and capital Y. So, these were the non-dimensional order 1 coordinates in the inner region. Now, in the outer region the non-dimensional velocity u is obtained by solving the potential flow equations, which I will denote by this function u outer of, now the order 1 coordinates here are x and y star. Now, in the intermediate region this can be written as some u intermediate of the order 1 coordinate which is capital X and now what we are calling capital Y intermediate. So, this is obtained by solving boundary layer equations. This is obtained by solving, I will simply say potential flow equations. This solution procedure I have discussed in the morning session. Now, this we will not solve separately, but will insist that both the approximations are going to give you a valid solution in the intermediate region. So, if you have a point somewhere here or here or here or here, you can look at the limit of the boundary layer solution which is u inner of this for large y, or you can look at the limit of the outer solution which is represented by u outer of this for small y star, and both will give you the good approximation. So, what is this function? Let us try and see. Now, we will express y intermediate in terms of y star which is the order coordinate, order 1 coordinate in the outer region. See, if here we have defined y intermediate the order 1. So, this is order 1, y intermediate is order 1 in the intermediate region, and that is defined as y star by epsilon to the power m. Y star by epsilon to the power m, which means that y star can be expressed as epsilon to the power m into y intermediate. And what we are trying to say is that in the intermediate region this coordinate is order 1. So, y star is order epsilon to the power m, which is what I had written earlier. Now, if you look at capital Y, this is as we have defined here y star by epsilon to the power half. It is a stretched coordinate which is order 1, y star is small. So, this is y star by epsilon to the power half. Now, y star we have shown is epsilon to the power m y intermediate by epsilon to the power half. So, one can write it as epsilon to the power m minus half y intermediate Now, m is less than half. So, this will be a negative number. So, I would prefer to write it as y intermediate by epsilon to the power half minus m. Okay. Recall that m is less than half and it is greater than 0. So, if I let p be half minus m, then this is going to be a positive number. So, this is y intermediate by epsilon to the power p. Now, what we will do is I want to express u intermediate of capital X and y intermediate. That is, I want to find this function without solving the equations, but by taking the say outer flow equations, let us say. So, as I said, the outer flow function u outer is going to be a valid approximation for this. Okay, so this will write as u outer of capital X comma instead of y star I will use this function epsilon to the power m y intermediate. So, what I have done is I have taken this function u outer of x comma y star, and instead of y star I have used this relation that y star is epsilon to the power m y and substitute here. So, I am expressing this arguments as x and y intermediate. Now, I can also take the have another representation for this u intermediate of x and y intermediate. Now, I can take the inner flow solution which was a function of x and capital Y. Now, I will express capital Y in terms of y intermediate. So, that is given here capital Y is y intermediate by epsilon to the power half. So, I will write it as x and y intermediate by epsilon to the power p. So, without resolving the equations in the intermediate region, we will just take the approximate solution in the outer region, express that y star in terms of y intermediate, and we can also take the inner flow solution and express capital Y in terms of y intermediate. Now, we insist that these two will give you the same result at least in the limit as epsilon goes to 0. So, this is what is called asymptotic matching. So, we will talk about what is called asymptotic matching. We will take the limit of u inner as epsilon goes to 0 of this function y intermediate by epsilon to the power p, and set it equal to the limit of the as epsilon goes to 0 of u outer of x comma epsilon to the power m and y intermediate. And in this limit process we are assuming that x remains order 1 and y intermediate remains order 1. So, we are equating the outer solution and the inner solution in the intermediate region. So, therefore, y intermediate remains order 1. Now, if this is a finite quantity which remains order 1, you are dividing it by a small quantity, remember p is greater than 0, then when you take the limit this becomes large, whereas here m is also greater than 0 and this is a small quantity. If this remains order 1 in the limit, then this becomes 0. So, this reduces to u inner x comma infinity equal to u outer capital X comma 0. So, this idea was first put forward by Prandtl and it is called Prandtl's matching principle. Now, more common way of stating this is this quantity u inner x comma infinity I can write as limit capital Y goes to infinity of u inner capital X capital Y. Remember that in the inner region or the boundary layer the order 1 coordinates are capital X and capital Y. So, if I take the limit of this function as capital Y goes to infinity, I get what I have here on the left hand side. Now, similarly the right hand side what you have over here is u outer capital X comma 0, we can write as the limit of u outer of capital X comma y star as y star goes to 0. So, in many books you will find this statement of Prandtl's matching principle, that as this limit of u inner of x comma y as y goes to infinity is the limit of u outer at x comma y star as y star goes to 0. Now, I will give you a physical interpretation of all this mathematics. What we are saying is that you have a plate here and a thin boundary layer, and you have a point which could be outside the boundary layer or slightly inside the boundary layer in the inner region. Now, suppose I have a point somewhere here, let us say a point P, it has a dimensional distance y p. Now, we have two non-dimensionalizations, one we are calling y star p, which is y p by L. Now, L is this large distance. So, if I show the L over here, this would be your L. So, y p by L is much less than 1. Now, you have another capital Y coordinate which we defined earlier, which was the same y p which you have over here, but this was non dimensionalized by delta naught, which is the this order of magnitude of the boundary layer thickness. Now, this is much greater than 1. Why? Because delta naught is small. Remember that delta naught is R e minus half into L, which is epsilon to the power half into L, and we are looking at a flow where R e is large, so epsilon is small. So, what we are doing is we are taking the outer solution for small y p and equating it to the inner solution for large y p. That is precisely the meaning of this term as mathematical form, that u inner of x comma infinity. So, you can think of this as x comma y p, capital Y p, which is much larger than 1, equal to u outer of x comma 0. So, this is the limit of y p star as y p star goes to 0. So, the non-dimensional coordinate, when it is non-dimensionalized by the outer length scale L, this is a small quantity because the boundary layer is thin. So, this point is very close to the plate, but this point could be outside the boundary layer also, it is the intermediate region. So, if you non-dimensionalize it by the order of magnitude of the boundary layer thickness, then it becomes a large quantity. So, this we will call u 0 of x. So, physically this represents the slip velocity at the wall obtained by solving the potential flow. So, when we solve the potential flow equations, we can only enforce the no penetration boundary condition, that is normal velocity on the plate is 0, we cannot enforce the no slip condition. So, when you find the solution and evaluate it at y equal to 0, you will see that this is not equal to 0, and that is the reason why the potential flow approximation fails to give adequate description of the flow near the boundary layer, because it cannot satisfy the boundary condition. So, when you solve Prandtl's boundary layer equation, which we had derived last time, we have to use these matching conditions. So, yesterday I simply wrote down the conditions without showing you the details, but those conditions were valid only for the flat plate, it is not valid in general. Today I am generalizing it to arbitrary flows. So, if you look at Prandtl's boundary layer equations, it is a system of equations. So, first equation that I am writing in dimensional form is the continuity equation or equation for local or differential conservation of mass. Then you have the approximate momentum equation, that is rho times u del del x plus v del del y operating on u equal to minus what we wrote as dp dx of x plus mu into del 2 u del y square. Here the term mu del 2 u del x square has been neglected, and the third equation was del p del y equal to 0, which I have already used by writing this del p del x as dp dx. Now, the boundary condition of the plate we have discussed yesterday at y equal to 0, the no slip condition which we could not enforce on the solution of the potential flow equations, we are going to set equal to 0, and v also equal to 0, that is a no penetration boundary condition. The other condition is the matching condition, which I will write this way: as y by delta naught goes to infinity, your u approaches u 0 of x. So, this is the inviscid flow slip velocity at the wall. So, this is obtained by solving the potential flow equations. Now, let us see how to find the pressure gradient. So, this equation I will rewrite with the pressure gradient on one side of the equation, I will move the other terms to the other side. So, we will write the momentum equation as dp dx, which is a function only of x, as mu into del 2 u del y squared of x comma y, this is in dimensional form, minus rho u x y del u del x x y minus rho v x y del u del y x y. Now, if you consider the three terms on the right hand side, each of them depend on x as well as y, but this sum total here will depend only on x. Now, I can evaluate this at any y and find what is dp dx. So, if I want, I could have put y equal to 0, but I do not know how to evaluate all the terms at y equal to 0, but from the matching conditions I know the conditions at infinity. So, I can determine the pressure gradient by looking at the conditions at infinity. So, this equation I can put any value of y, here we will put y equal to infinity. So, mu del 2 u del y squared of x comma infinity minus rho u x comma infinity del u del x x comma infinity minus rho v x comma infinity del u del y x comma infinity. The reason I am doing is that we can find out, evaluate the right hand side for when I put y equal to infinity. Now, it is an asymptotic conditions that u goes to a u x comma infinity is u0 of x. So, if I differentiate it, I have del del x of u x comma infinity is du0 dx. So, this term is known, it is du0 dx, and this term is u0, and as we have discussed yesterday, this term is 0 because it is an asymptotic condition that as y goes to infinity, u is asymptotically approaching u0 of x. So, the slope and the curvature, they are all going to go to 0. So, finally, what we come up with is this dp dx is equal to minus rho u0 of x into du0 dx. So, if you can solve for the potential flow, if you can solve the potential flow equations in the outer region, you can find what is u0 of x, and if you multiply u0 x by du0 dx and multiplied by minus rho, you get what is the pressure gradient inside the boundary layer. Now, for the flat plate, this was a constant u0 x, it was independent of x. So, du0 dx was 0. So, we had shown last time that it is 0, but last time of course, I did not show you that it is a constant. So, why we are doing all this analysis is to answer the question, what is the utility of potential flow in predicting the flow of real liquid fluids. So, I will summarize it this way, what is the utility of potential flow analysis? So, what I will say is that it is useful in or predicting viscous flows, that is flows of real fluids. When the Reynolds number is large. So, when R e is much greater than 1, viscous effects are important only in the boundary layer. When R e is much greater than 1, viscous effects are negligible in the outer region. So, solution of potential flow equations gives an adequate approximation of viscous flow in the outer region. The potential flow analysis cannot predict the flow inside the boundary layer, but the flow outside the boundary layer can be determined by solving the potential flow equation. Now, when you want to find or predict the flow in the boundary layer, so potential flow analysis helps in the solution of the boundary layer equations. Provides the following information about the following information for solution of Prandtl's boundary layer equations. It gives you two things, one is the velocity at the edge of the boundary layer, So, the boundary condition that as y goes to infinity, or you can say u goes to u 0 of x, this u 0 is determined from the potential flow analysis. The second thing it tells you is the pressure gradient inside the boundary layer. We are showing that dp dx in dimensional form is minus rho u 0 x du 0 dx. Now, if you are interested in the this, you can write as y by delta naught if you want to write it in dimensional form. So, if you go back and look at Prandtl's boundary layer equation, you are going to solve only these two equations. So, now there are two unknowns, u and v, and there are two equations. This quantity is not an unknown, this is known and this is predicted by the potential flow analysis. Similarly, this quantity also is predicted by the potential flow analysis. Excuse me. So, let us simply complete the potential flow analysis for the plate. We have seen that del 2 psi del x square plus del 2 psi del y square must be 0. This we showed in the morning session, and we showed that on the plate psi is a constant. So, if you want, you can set the constant equal to 0, and upstream is a uniform flow with speed u infinity. Now, recall that u is del psi del y. So, if u is infinity here, then psi will be like u infinity into y plus a constant which I am setting equal to 0. So, you want to solve this equation with the boundary conditions that as x goes to minus infinity far upstream of the plate, your psi approaches u infinity y, and at y equal to 0 psi is 0. Now, if you consider a function, say f of x y, which is simply u infinity y, let us say, it does not depend on x, then you can see that if I put y equal to 0, this is 0. So, this boundary condition is satisfied. Now, this quantity, this function u infinity y satisfies the upstream condition. Let us see whether it satisfies the equation. So, what is del f del x? Well, del f del x is 0 because this does not depend on x. So, del 2 f del x square is also equal to 0. Now, if I look at del psi del f del y, that is u infinity, which is a constant. So, if you look at the second derivative del 2 f del y squared, that is 0. This implies that del 2 f del x squared plus del 2 f del y squared is 0. So, this function satisfies your Laplace equation, it satisfies the required boundary conditions. So, therefore, we can say that the solution is simply u infinity times y. So, the potential flow solution for the plate, flat plate. So, if this is your plate and the upstream flow is a uniform flow, then you have the potential flow solution in terms of the stream function, this is equal to E infinity y. This is now holding for at all points in the outer region. Now, if you want u, that is del psi del y, which is U infinity everywhere. So, if you draw the velocity profile here obtained by solving the potential for equations, it will be the same profile upstream as you have upstream, U infinity. I can draw it at another section here, it will be the same profile. So, this is U infinity, this is also infinity, and V is minus del psi del x, which is 0 everywhere. So, the streamlines remain parallel lines. This is the prediction of the potential flow solution. Now, what is important for as far as the boundary layer analysis is, what is u 0 of x? This is nothing but u potential of x comma 0, that is at y equal to 0, but here saying that u is a constant everywhere. So, this is simply u infinity. Now, du 0 dx is going to be 0, which means that dp dx is 0. So, this is the condition I had stated yesterday, that if you look at high Reynolds number flow past a flat plate which is aligned with the direction of an uniform oncoming free stream, the pressure gradient to a first approximation is 0 inside the boundary layer, and the velocity at the edge of the boundary layer is u infinity. But there could be cases where u 0 is not a function of is not a constant, but a function of x. So, this is an example of what you call the 0 pressure gradient boundary layer. So, if you look at dp dx inside the boundary layer, that is minus rho u 0 into du 0 dx. Now, we know that rho is always positive and u 0, the slip velocity usually is positive. This can be either plus or 0 or minus. So, you can have 3 cases. Case 1 is u 0 x equal to constant, that means du 0 dx is 0, which means that dp dx is 0. This is the case we have already seen. So, this is what we are calling 0 pressure gradient boundary layer. Now, you could have a second case where du 0 dx is positive. So, this is an accelerating outward flow. Now, if this du 0 dx is positive, then dp dx will be negative. So, this is what is referred to as favorable pressure gradient. The reason why we are calling it favorable pressure gradient will become clear if you show the fluid forces due to pressure on a fluid element. Let us say the flow is this is the x direction. So, you have a particle, let us say, of this shape, the particle is moving in the x direction. Now, you have pressure forces on this left face, pressure forces on the right face. If dp dx is negative, it means that the pressure is falling in the direction of the flow. So, you have a large pressure on this left face and a small pressure. The pressure is always acting normally and it is a compressive force. So, on the left face it will act in the positive x direction, on the right face it will act in the negative direction. dp dx is negative. So, this magnitude of this arrow, the length of this arrow which represents the magnitude of the pressure is larger than the length of this arrow here. This is of course an exaggerated view, but you can see that the net force due to pressure is in this direction. So, this is the net force due to pressure. So, if I call this the left face, this is a PL, or this is the right face which I call PR. So, this is PL minus PR into the area of this face over here. and here this is positive. So, this is the net force is positive and it is acting in the same direction as the motion of the particle. So, it is aiding the motion of the particle or favoring it, that is why it is called favorable pressure gradient. Now, we can have a case 3 where du 0 dx is negative. So, this is a case where the outward flow is decelerating. Now, your dP dx is going to be positive. Now, this is referred to as an adverse pressure gradient flow. Again, to see the implication of this, let us consider the forces on a fluid particle whose spaces are parallel to the coordinate axis. Now, here dP dx is positive, the fluid is flowing in the positive x direction, that is the fluid flow in the inside the boundary layer. Now, the pressure is falling in the direction of the flow. So, pressure on the pressure is increasing in the direction of the flow because dP dx is positive. So, here we will have a situation where the pressure here is larger than the pressure here. So, if I show the arrows, this is the pressure on the left face, let us say, and this is the pressure on the right face. So, if you want the net force on fluid element, due to pressure in x direction, this is again going to be PL minus PR into the area, but now you see that PR is larger than PL. So, this is negative. So, the net force due to pressure, if I show by this double arrow, is going to be in the negative x direction, it is opposing the direction of motion of the fluid. So, it is called an adverse pressure gradient. Now, if this adverse pressure gradient is very large, it may lead to reverse flow near the wall. So, that is what is called boundary layer separation. So, this will occur when there is a large adverse pressure gradient. Now, unfortunately, if the boundary layer separates, the boundary layer approximation is not valid beyond the separation point. So, all this idea of Prandtl of dividing the flow field into two regions and making two different approximation two regions, that will fail. However, you can use it to predict roughly the location where the separation takes place. Now, I will come back and answer one question which was asked before when I talked about the Venturi meter. So, that was a converging diverging duct. So, that was an internal flow, but even in internal flows you may have boundary layers. So, the question which was asked by 3 times to me is, why is the angle of divergence less over here? Now, here what will happen is, you will have boundary layers growing on both the walls, and what we were calling the outward flow. Now, you can do an analysis similar to that and solve Prandtl's boundary layer equations in the boundary layer, and then you have to match with, not with the, you have to match with what is called the core flow or the flow in the core region. So, this is the equivalent of the outer region for external flows. Now, if you neglect the thickness of the boundary layers, which are very thin at high Reynolds number flows, you can see what is happening here to the core flow. So, if you assume that you have an approximation where the velocity can slip along the wall, you have some V naught velocity coming here. because the area is reducing and the volume flow rate is the same, here the velocity will increase. So, this is like an accelerating order flow. So, in the converging part your u0 du0 dx, if I say this is the x direction of flow, is going to be positive. So, you are going to have dp dx negative. So, this is the region of adverse favorable pressure gradient. Now, the same volume flow rate is passing through the diverging section. So, as you move downstream here, the area is increasing, but the flow rate is the same. So, the velocity will decrease. So, if you show a typical velocity profile here, this magnitude will be less than your V naught. So, in this diverging section here, you are going to have du0 dx negative, that is the core flow is decelerating, which means that dp dx is going to be positive, and you have an adverse pressure gradient. And what might happen is the moduli might separate and you may have a flow inside the moduli which is in the opposite direction to the main flow. So, if this is a point of separation over here, the fluid may come in the opposite direction and move over here. So, you have what is called a flow reversal, and once you have a recirculating region over here, there is some kinetic energy associated with that. So, the losses will increase, and that is what you want to avoid. So, I hope by now the utility of the potential flow analysis is clear and its relevance to the flow of viscous fluids. So, let us go on and move on to other things. We will look at say potential flow past a cylinder, 2D potential flow over a cylinder. So, we have done it for the flat plate, now we will do it for a cylinder. So, what you have now is a solid cylinder, and we will put a coordinate system now with origin at the center, and this cylinder we will consider to be a cylinder whose length is very large in the z direction. So, you can take it to be a 2D body, and the upstream flow we will take to be an uniform flow, and we will choose a coordinate system where the x direction is in the flow direction. So, this is your upstream flow. So, if you look at the streamlines upstream, they are all parallel lines. So, the V is 0 upstream and u is u infinity. So, infinity is the speed of the flow. Now, if it is potential flow, we have seen that we can get a solution for the stream function by solving the 2D Laplace equation. Now, we have to apply boundary conditions on the surface of the cylinder. So, if I say the radius of the cylinder is a, then you have this condition that at r equal to a, the radial velocity is 0. So, here it is preferable to use cylindrical coordinates. So, if you have a point in the flow region, if you connect it to the origin by a straight line here, this distance is what we call the radius, and this angle from the x axis we will call theta. So, if I want to describe the coordinates of this point P, you can use the Cartesian coordinates x, y, z, or the polar cylindrical coordinates r, theta, z. Now, we are considering 2D flow where del del z is 0 of any flow quantity. So, we will simply talk about polar coordinates r, theta. Now, we will write Laplace equation in cylindrical coordinates. So, you are going to have del 2 psi in polar coordinates del 2 psi del r squared, and then you have a first order term 1 by r del psi del r, and you have a term involving del 2 psi del theta squared. Now, all these terms have the units of psi by r squared, and you have a scale factor here which is exactly 1 by r squared. So, this is a 2D Laplacian in r theta coordinates. So, we want to find a solution of this equation. which satisfies the upstream condition of a uniform flow. Now, let me show the V r and V theta components. So, if you have a fluid E r as a unit vector in this direction, it is a unit vector pointing radial outwards, and you have another unit vector we will call E theta, which is perpendicular to this, and it is pointing in the direction of increasing theta. So, the velocity vector I can write as V r E r plus V theta E theta plus you are going to have V z E z. E z is the same as k. So, E z is the same as the what we were earlier calling k. Now, it is a 2D flow. So, for this case V z is 0. So, a flow in the x y plane, you can either use the V x V y components or the V r V theta components. Now, if you look at the continuity equation, you can find the expression for V r and V theta in terms of the stream function. But before we do that, let us look at the boundary conditions for this. So, we will consider a point with reference to an origin. Let us say this is the origin and this is the position vector of a point P. Now, suppose the velocity here at point P is uniform and in the x direction. So, this is a velocity vector which is say u infinity I. So, this is x, this is y, this is r, and this angle is theta. Now, to find the radial and azimuthal components, you have to complete this vector triangle. So, drop a perpendicular from here onto this radial line. So, this angle is 90. Now, the length of this arrow is the magnitude of the velocity, which is u infinity, and this is your angle theta. So, you can see that this distance here is u infinity cos theta, and this velocity is u infinity sin theta. So, this vector v I can write as the sum of this vector plus this vector by the triangle law. So, this is the radial component of velocity, and this which is positive, as you can see, is pointing in the direction where r is increasing, and this is the azimuthal velocity component, but is pointing in the direction of where theta is decreasing. So, this is negative. So, you see that this you can write as u infinity cos theta E r minus u infinity sin theta E theta. So, the radial and azimuthal or swirl velocity components here will depend on the angle for the case of a uniform flow. Now, far away from the cylinder, the velocity will become uniform, because the cylinder will not affect the flow at infinity. Upstream the flow was a uniform flow, downstream and far away from the cylinder it will remain a uniform flow, since this is an inviscid flow. Now, we will look at the expression for divergence of V in cylindrical coordinates. So, that is 1 by r del del r of r V r plus 1 by r del V theta del theta plus del V z del z. Now, for us the z component is 0. So, this is not there. So, conservation of mass tells you that this is equal to 0. Now, I can you have the 1 by r factor here and here. So, that can be dropped and we can write it as del del r of r V r plus del of V theta del theta is 0. So, from here you can define a stream function such that r V r is del psi del theta. So, this term here will become del 2 psi del r del theta, and your V theta will write as minus del psi del r. So, that the second term becomes minus del 2 psi del 2 psi del theta del r. So, by introducing this stream function, the continuity equation is identically satisfied. So, this tells you that V r is 1 upon r del psi del theta and V theta is 1 by minus del psi del r. So, V r we will say is 1 upon r del psi del theta. So, we have these conditions that as r goes to infinity, r is the radial distance from the center of the cylinder, the V must become u infinity I, a flow in the x direction. So, we have seen that V r, which is 1 by r del psi del theta, will approach u infinity cos theta, and V theta, which is minus del psi del r, this will approach minus u infinity sin theta. So, we will have to solve this Laplace equation subject to these conditions and infinity, and of course, at r equal to a, your V r, which is 1 by r del psi del theta, this must be equal to 0. This is the no penetration boundary condition. Now, you can get a solution using separation of variables. I will not go into the details of the general method, but you can see that these boundary conditions suggest that psi has a factor which is sin theta. So, we will try out a solution of this form. Psi of r theta is some function of r only into sin theta. Now, this will be able to satisfy, this form will satisfy these boundary conditions, because from here you see that V theta will be minus del psi del r, which is minus df dr sin theta. So, that means we can say that as r goes to infinity, your df dr will approach u infinity. If df dr approaches infinity as r goes to infinity, it will satisfy this condition. Similarly, if I look at V r, that is 1 by r del psi del theta. So, if I differentiate this, you are going to have 1 upon r df dr cos theta. So, now as r goes to infinity, sorry, it is f by r cos theta. As r goes to infinity, if f by r approaches u infinity, then this condition is satisfied, and at r equal to a, your V r must be 0. So, f must be 0. So, what we will do is we will take this form and substitute into that equation. So, we are going to try out this solution of this form psi r theta is a function of r only into sin theta. This form can satisfy the boundary conditions, just a single function like this. Now, if I substitute over here, these two are partial derivatives keeping theta constant. So, we are going to get simply d2 f dr squared plus 1 by r df dr into sin theta from the first two terms. Now, here in the second term, you are going to differentiate it twice with respect to theta. So, if you take sin theta and differentiate it twice, you will get minus sin theta. So, you are going to have minus f by r squared sin theta equal to 0. Now, the sin theta factor can be taken as a common factor, and you are going to have d2 f dr squared plus 1 by r df dr minus f by r squared equal to 0. So, for this to hold for all theta, this quantity in parenthesis must be equal to 0. So, we have an ODE, ordinary differential equation for f of r, which you can solve to find f. Now, here it is convenient if you multiply this whole equation by r square, you can write it as r square d2f dr square plus r df dr minus f equal to 0. Now, you can recognize this as the Euler-Cauchy equation, or some others call it equidimensional equation. So, here what you are doing is you are differentiating once with respect to r and multiplying by r. Here you are differentiating f twice with respect to r and then you are multiplying by r square. So, equation of this has solutions, a homogeneous equation of this form where the right hand side is 0 has solutions of the form say r to the power p, where p is a constant. Now, let us see whether we can find p by substituting this into this equation. If r is r to the power p is a fundamental solution of this, then df dr will be p r to the power p minus 1. So, therefore, r into df dr will be p r to the power p. So, here in this term minus f term you have r to the power p, and here also you are getting back r to the power p. Now, if you look at say d2f dr square, df dr is p into r to the power p minus 1. So, d2f dr square you get by differentiated again. So, p into p minus 1 r to the power p minus 2. So, once again if I multiply this by r square, you are getting back r to the power p and of course multiplied by this constant. So, if f r is r to the power p, then r squared d2f dr squared plus r df dr minus f. So, this whole quantity is the left hand side of this equation which you want to solve. This will become, you can factor out r to the power p, which is because it is occurring in each of the 3 terms. Here you get p into p minus 1, and here you are going to get p, and there is a minus 1 coming from here. So, if you look at this, is p squared minus p plus p minus 1 into the r to the power p. This is p square minus 1 into r to the power p. Now, r to the power p is not 0. So, p square minus 1 must be 0, or in other words p minus 1 into p plus 1 is 0. So, there are 2 values of p which satisfy this initial equation p square minus 1 equal to 0. One is p equal to 1, the other is p equal to minus 1. So, you have 2 solutions, 2 fundamental solutions, 2 fundamental solutions of this equation. R to the power 1 and r to the power minus 1 or 1 upon r. So, the general solution f r will be a linear combination of the 2, say some constant a into the r to the power 1 plus another constant b into r to the power minus 1, or we can write it as a r plus b upon r. So, in other words we are saying that psi r theta must be of this form a r plus b by r into sin theta. Now, let us see whether we can find the constants a and b. Now, if you look at say V r, that is 1 by r del psi del theta. So, if we divide by r, this becomes a plus b by r squared cos theta. This cos theta is coming when you differentiate sin theta. Now, on the surface of the cylinder, that is at r equal to a, V r will be a plus b upon a squared cos theta. This must be equal to 0 for all angles. That means a plus b capital B by small a square must be 0, or b will be equal to minus a squared into a. So, I can write psi then, psi of r theta by factoring out the a into r minus a squared by r into sin theta. Now, V r will be a into, you have to divide by r and differentiate with respect to theta, 1 minus a square by r squared sin theta. And you can see that if I put r equal to a by r is 1. So, a by r whole square will be 1 square. So, 1 minus 1 is 0, it satisfies the no penetration boundary condition. Now, take the limit as r goes to infinity. As r goes to infinity, V r will approach a sin theta, because you have r in the denominator. So, this will go to 0, but this must be equal to u infinity sin theta. Sorry, I forgot this cos here, you have to differentiate, this is cos. So, this approaches a cos theta, which is u infinity cos theta. So, that means that a must be equal to u infinity, and you can see that if you look at V theta is minus del psi del r. So, this will also satisfy the other boundary condition. So, let us make a summary now. We have got psi of r theta is, we have found what is a, it is u infinity into r minus a square by r sin theta. So, we have found the stream function for flow past a cylinder. Psi of r theta we have found is u infinity into r minus a square by r sin theta. Now, let us find the velocities. V r from this expression, V r is 1 upon r del psi del theta. So, when you differentiate partially with respect to theta, this sin theta will become cos theta, and if you divide by r, this becomes 1 minus a square by r square. So, this is u infinity into 1 minus a square by r square into cos theta. As you can see, if I put r equal to a, V r is 0. So, it satisfies the no penetration boundary condition, and if you take r going to infinity, this V r approaches u infinity cos theta. Now, V theta is minus del psi del r. So, here this will, theta dependence will be simply sin theta, and if I differentiate this, you get 1 plus a square by r square. So, you have minus u infinity into 1, and this is r to the power minus 1. So, if you differentiate, you get minus r to the power minus 2. So, this is plus a square by r square into sin theta. Okay. Now, you can check out the conditions at r equal to 0, V r is 0, that is satisfies. As r goes to infinity, for V r approaches u infinity cos theta, and V theta approaches minus u infinity sin theta as this term goes to 0. Now, I will show you the conditions which we had found here. For the case of the uniform flow, we had argued that V r should approach u infinity cos theta and V theta should approach u infinity sin theta, and that is exactly what we have over here. So, this solution which we have found satisfies the boundary conditions at infinity as well as the boundary conditions at the wall. Now, let us see how to find the pressure. So, in pressure to find the pressure we have to use Bernoulli's equation. So, we have to find what is the magnitude of the velocity square. So, what we will do is look at Bernoulli's equation. Or before that, let me plot the streamline pattern or the lines of constant psi. You can see that if you put r equal to a, your psi of a comma theta will be u infinity a minus a square by a sin theta, which is 0 for all theta, because this is a minus a. Now, you can see that when theta is equal to 0, psi of r comma 0 is 0. Again, when theta is equal to pi or 180 degree, psi of r comma pi is equal to 0. So, if I want to draw the psi equal to 0 streamlines, you see that the surface of the cylinder is a line where psi is 0, and this line which represents theta equal to 0, and this line which represents theta equal to 0. So, these are the psi equal to 0 lines. Now, you can anticipate that this will be a stagnation point, because two streamlines have met at this point here and here. So, the flow is in this direction. So, this will call the forward stagnation point and this will call the rear stagnation point. Now, I can put psi equal to some constant and you will get a streamline which goes like this. And if you look at the streamlines below, they will be like this. So, this streamline pattern is symmetric. So, if you take put a mirror over here, the pattern on this side and the pattern on this side will be mirror images. Similarly, if you put a mirror here, the pattern above and the pattern below will be the same, and at very far distances from the cylinder, the streamlines will become straight lines. So, this is the streamline pattern. Now, let us find what is the stagnation pressure here. We know that Bernoulli's equation will apply along can be applied between any 2 points. Now, we have found the expressions for V r and V theta. So, let us look at V r of a comma pi. So, those are the polar coordinates of the forward stagnation point. Remember, the origin was here at the center of the cylinder, this was x, this was y. So, here the radius is a and the angle is 0, and here the radius is a and the angle is pi. So, V r of a comma pi here, you have put r equal to a, that is the point on the surface of the cylinder. So, that is 0, and if you look at V theta of a comma pi, that is also 0, because sin theta is 0. So, both the velocity components are 0 at what we are calling the forward stagnation point. Now, similarly, if you look at V r of a comma 0, that is the rear stagnation point, V r anyway is 0 because r equal to a. If you look at V theta of a comma 0, that is 0 because of this sin theta term. So, this sin theta term is 0 at when theta is pi or theta equal to 0. So, what we anticipated is correct, we have verified it that both the velocity components here are 0. Now, let us see what is the velocity on the surface of the cylinder. Well, V r is 0, but V theta is not 0, and the fluid is flowing this way along the top of the cylinder. So, V theta is negative because we are counting theta to be positive from this x axis, this is a positive x direction, and the fluid is flowing in the anti-clockwise direction. Sorry, the fluid is flowing in the clockwise direction. Now, what we want then is to look at this expression and find V theta when r equal to a. So, you see that V theta of a comma theta will be, if I put r equal to a, this is a square by a square. So, 1 plus 1 is 2, that is minus 2 u infinity into sin theta. So, this is the velocity V theta on the surface of the cylinder. So, I can write it as V theta s, and of course, V r s is 0 because of the no penetration boundary conditions. So, if I say P s is the pressure on the surface of the cylinder, of course, P s will be a function of theta, because on the surface of the cylinder r is a constant which is a, and as you move along the surface of the cylinder theta is changing. So, you are going to have in general P plus half rho, and V square I can write as V r square plus V theta square. And here you can write minus rho g dot r on the body force is a constant, or you can combine this small p and this minus rho g dot r and call it the piezometric pressure. In many cases this may be negligible, so you may not be interested in this, or you may be applying this equation between 2 points on a horizontal streamline. So, the change in potential energy may be 0. Now, if you look at evaluate this on the surface of the cylinder, you are going to have P s plus half rho V r s squared plus V theta s squared minus rho g dot r s whatever is the same constant. The first term is 0 and the second term we have already found. We have shown that V theta s is minus 2 infinity sin theta. So, let it here again, V theta s is minus 2 u infinity sin theta. So, V theta s squared will be 4 u infinity squared sin square theta. Now, this constant can be evaluated from the upstream conditions. So, you can say that this upstream the velocity is magnitude is u infinity. So, you can say that P s plus half rho V theta s squared is equal to P infinity plus half rho infinity squared. Now, if you want to account for the body force, you can interpret this as the piezometric pressure capital P infinity, and this is as a capital P on the surface of the cylinder. So, P s minus P infinity will be half rho infinity squared minus half rho, and V theta squared you are getting is 4 u infinity squared sin square theta. All I have done is move this term to the left hand side and this term to the right hand side. Excuse me. So, P s one can write as P infinity plus half rho infinity squared into 1 minus 4 sin square theta. So, this tells you how P s varies with theta. So, P s is a function of theta. Excuse me. So, what I have done is I factored out this infinity squared and taken a common factor. Now, you can define the coefficient of pressure C p as P s minus P infinity by half rho infinity squared. So, this will turn out to be equal to 1 minus 4 sin square theta. So, this is a function of theta. Now, I will show this on a figure, so that you can correlate it. This is a cylinder. You have a point on the surface of the cylinder and this is the angle theta, and the fluid is flowing from left to right. So, theta is the angle measured from the rear stagnation point. Now, when you do experiments, you may want to measure angle from the forward stagnation point. So, this angle you may call theta prime. So, if we define theta prime to be pi minus theta, this is the angle measured from the forward stagnation point, then you can express C p as a function of theta prime. Now, sin of pi minus theta is the same as sin theta. So, C p is also equal to 1 minus 4 sin square theta prime. So, I will plot C p versus theta prime and then we will have a T break. So, if this is the C p axis versus theta prime. So, let us say this is pi 0, pi by 2, pi 3 pi by 2 and 2 pi. When theta prime is 0, C p will have a value of 1. Now, when sin theta is 90, this will be 1 minus 4, which is minus 3. So, I will put minus 1 over here, minus 2 over here and minus 3 over here. Now, when theta is pi by 2 or theta prime is pi by 2, that is, you are on the top of the cylinder, this is minus 3. And when theta is pi, so you have a curve which goes like this. We are not interested in what is happening here, because it is symmetric. So, what you are doing is, this is the cylinder and you are measuring angle from the forward stagnation point. This is my theta prime and this is the direction of the flow, upstream flow. So, upstream flow is in this direction. So, C p is has the maximum value at this point when theta prime is 0 and the minimum value here when theta is pi by 2, that is here. And inviscid flow theory, potential flow theory is predicting that the pressure will recover to its previous value So, the pressure at the forward and rear stagnation points according to potential flow theory is the same, and those are the maximum points of maximum pressure. The point of minimum pressure is the top of the cylinder or the bottom of the cylinder. The flow pattern is symmetric. Now, as you can see that if you look at the velocity, slip velocity along the surface, it is 0 here and is 0 here. It is accelerating from 0 to a maximum velocity here, which is minus 2 infinity, and then it is decreasing again to 0. So, the magnitude of the velocity, slip velocity on the surface of the cylinder goes from 0 to 2 infinity, twice the u infinity, and then it decelerates back to 0. So, this part is an accelerating flow and this part is a decelerating flow. So, here you will have a favorable pressure gradient and here you will have an adverse pressure gradient. So, according to potential flow theory, flow separation is likely to occur on the rear side. Now, in practice, of course, once the flow separates, the Bonnet theory is not valid. So, we cannot get a very accurate prediction of the point of separation from here. So, while potential flow theory will tell you that separation might occur between angle of 90 and 180, it actually occurs around 85 or so. But if you compare this with experimental data, you will see that there is a good agreement with Bonnet theory somewhere here, and then it will start to deviate. So, once the flow separates, you will have a wake region where the pressure is approximately constant. So, if you look at laminar flow, past a cylinder, this is cross flow, the separation might occur somewhere here and you will have a broad wake region where the pressure is approximately constant. So, if you show it over here, in this region the pressure goes like this and it does not recover to the old value.